Okay, welcome to the Graphs and Matroids seminar. Today we have Rose, and she's going to tell us about coloring visibility graphs.
Thank you, Jim. So everything I'm going to talk about today is joint work with James Davies and Tomasz Krawczyk and Bartosz Walczak. So James and I are both PhD students of Jim, and we had the chance to visit Tomasz and Bartek about a year ago in Krakow to do this work. And so I'm excited to tell you about what we've been working on. So to begin with, we're going to consider a set of points on a Jordan curve. And we're always going to assume that this set is finite, but also that it's in general position. So I just don't want to stop myself as I'm going through to say when we need the general position assumption. So I'm just going to make it right at the very beginning. And from there, we say that 2 points A and B are mutually visible if the open line segment between them is contained in the interior of the Jordan curve. And that defines a visibility graph. So the way that you should think about this, or sort of the motivation for this, is that the Jordan curve is the walls of the room, and you're putting people at different points along the walls of a room, and then you're just putting an edge between two people if they see each other. And the walls aren't clear or anything. You can't see through walls, so the edge has to be totally contained in the interior. And the theorem that we've proven is that any visibility graph with Clique number omega has chromatic number at most 3 times 4 to the omega minus 1. So this is an approximate characterization theorem for the chromatic number of a visibility graph. And so what is the clique number of a visibility graph? Well, usually a clique is the size, a clique is a set of pairwise adjacent vertices, and the clique number is the largest size of the clique. But in a visibility graph, there's a really nice geometric interpretation. So a clique is exactly a set of vertices whose convex hull is contained in the interior, except for at those particular points. So here's one maximum clique in this graph, and here's another maximum clique, and the final maximum clique. And then the chromatic number of a graph is the smallest number of colors. You can color every vertex so that no two vertices of the same color see each other. So if you look at, say, all the blue stars, this is a stable set in the graph. And I'm going to write throughout the talk chi for the chromatic number of a graph. And in general, you always get that omega is at most chi because you have to use a different color for each vertex in a maximum clique. So you get this really easy lower bound on the chromatic number, but it's usually difficult to see why the chromatic number is large. So for general graphs, the chromatic number can be arbitrarily far away from the clique number. And so it's really nice to say that you also get this easy upper bound on the chromatic number. I like to think of it as really a characterization for the chromatic number because it's easier to see a clique in a graph than it is to see why the chromatic number is small or large. And so we say that a class of graphs is chi-bounded if there exists some function f, so that for every graph in the class, its chromatic number is at most that function of its clique number. And so this just helps us to talk about this property. And so the question of whether visibility graphs are chi-bounded was already open for a subclass of visibility graphs. So there's a really nice subclass, which is studied more often in computational geometry, called Polygon visibility graphs. And these are exactly visibility graphs where consecutive vertices along the Jordan curve are adjacent. And then those edges between consecutive vertices always define a polygon. And in fact, the polygon itself is enough to tell you all of the information about visibility in a graph. You can get rid of the Jordan curve and just keep track of the polygon. And so Karapur and Wood asked if polygon visibility graphs are chi-bounded. And so this is a positive answer to their question. But what makes visibility graphs nice and a property that polygon visibility graphs don't have is that visibility graphs are hereditary. So a class of graphs is hereditary if it's closed under deleting vertices. And if you take a visibility graph and you try and delete a vertex, it doesn't change the notion of visibility between other vertices. And so that graph is still a visibility graph. You can keep on going, this is still a visibility graph, but it's certainly not a polygon visibility graph because it's disconnected. And polygon visibility graphs always have a Hamiltonian cycle. So this class that we're considering is just really like naturally the hereditary closure of these polygon visibility graphs. So I want to talk about like the main reasons why we're interested in this theorem. And the first reason is going to have to do with chi-boundedness. So chi-boundedness is a really sort of classical concept in graph theory. Even if you look at Weising's theorem, you can interpret Weising's theorem as saying that the class of line graphs is chi-bounded by omega plus 1. And there's a long history of studying chi-boundedness. And our results is the first result that takes a class of visibility graphs that's hereditary and shows that it's chi-bounded. So there have been some other negative results in the past, but ours is the first positive result. And you can look at visibility of different types of objects and not just points on a Jordan curve, but you could take, say, you could take your vertices to correspond to, say, convex subsets of the plane, or to line segments, or to points. And you can take your notion of visibility to be lots of different things. Maybe you're forced to only look in vertical line segments or something like that. And your obstacles that block visibility can also be lots of different things. It doesn't have to just come from a Jordan curve. And so there's a rich literature on visibility graphs, and we hope that this result will lead to more results for different types of visibility graphs. And the reason why this is particularly interesting is because there's lots of other geometric ways of defining chi-bounded graph classes. I've just listed a subset. There's certainly many more than this. I'm going to be missing a lot still. But all of these examples that I have listed and all that I know of for geometric chi-bounded classes all arise from intersection and disjointness graphs of curves in the plane. So for these graphs, you start with a collection of simple curves in the plane, and you add a vertex for each of those curves. And then to get intersection graphs, you add an edge between each pair of curves which intersects. And to get disjointness graphs, you look at the complement of that. So you add an edge between each pair of curves which are disjoint. So the point is that all of these graphs above are intersection graphs and disjointness graphs of curves. And so there's a nice way of understanding all of these other results through a common framework. And that framework doesn't apply to visibility graphs. And so it seems like they're really a new example, although it's still sort of open and we're still trying to understand exactly how new of an example it is. Another thing I'd like to notice is that you are probably already familiar with this, even if you don't realize it, because interval graphs are intersection graphs of curves in the plane. And lots of other really common types of perfect graphs like chordal graphs and comparability graphs and co-comparability graphs all can also be represented this way. So one other thing about this is that the class of intersection graphs of curves in a plane isn't as a whole chi-bounded. You have to go to certain subclasses in order to make it chi-bounded, but we still understand that rather well. There's a result of Rock and Walczak that applies to all of these classes. And it says that if you have a class of intersection graphs of curves in the plane, so that all of those curves intersect the x-axis at least once and at most t times, then that class is chi-bounded. So we'd like to eventually, at some point, have a more general understanding of which visibility graphs are chi-bounded. But so far it seems new. It's different from the other classes that we know of. And the second main reason is that polygon visibility graphs are really fundamental in computational geometry. So even if you're given a polygon and you want to triangulate it, that's the same thing as finding a maximal outer planar subgraph of the visibility graph. And so there's a lot of work going into representing these graphs. How much precision do you need to store the vertices of your visibility graph without changing the graph itself? And all this sort of thing. What's the complexity of determining the visibility graph from the polygon? And in this direction, it's been shown that it's NP complete to test if the chromatic number of a polygon visibility graph is at most 5. But yet, the Clique number can be computed efficiently. And so if you see this, this is really tempting because our result gives you these upper and lower bounds in the chromatic number in terms of the Clique number, and the Clique number can be efficiently computed. So we'd like to use this to get an approximation algorithm for the chromatic number. But there's a little bit of a technical difficulty here, which is that you'd like to have a nice representation of your graph, and you would rather not deal with this Jordan curve. You'd like to know how many bits it takes. So you'd like your algorithm to be polynomial in the number of vertices of the graph. And it's not even clear whether or not our representations are polynomial in the number of vertices of the graph. But Ghosh, Shermer, Bhattacharya, and Goswami gave a nice way of dealing with that. So their algorithm works whenever the input just takes the graph as an abstract object and the Hamiltonian cycle, which corresponds to the polygon. So you don't need the actual representation of the graph, you just need the graph and this Hamiltonian cycle. And so we can do the same thing for curved visibility graphs. We don't have a Hamiltonian cycle, but we can take our curved visibility graphs and we can order the vertices cyclically. And just keep track of that information. So here's the graph itself and the order of the vertices cyclically. And we've been able to show that if you're given that as input, that we can do the same thing in polynomial time. So we can compute the Clique number exactly. And we can also find this 3 times 4 to the omega minus 1 coloring. And so that gives us an approximation algorithm for the chromatic number. Now, there's one other thing which I think is really interesting about this, which is that we haven't even been able to rule out using this approach to get a constant factor approximation for the chromatic number, which is of course what you want. So we know that this constant can't be better than 3/2, but as far as we know, there could still be a constant. So I'll talk about this a little more at the end. So ideally, you'd like an algorithm that doesn't take as input a visibility graph, but instead it takes in a graph with the cyclic order through the vertex set, and it tells you whether or not that is a visibility graph. So this is called the recognition problem of whether or not there's an algorithm that takes in this ordered graph and tells you if it is a visibility graph. And there, I'd conjecture that the recognition problem is NP-hard. So this conjecture is a little bit bold. I haven't been able to find this conjecture in the literature, even though this recognition problem has been studied since the 80s. And there's a lot of literature on it. So I'm being bold to make this conjecture. But for the matroid union seminar, I want to do this because there's a reason for why this is. It has to do with oriented matroids. So let me say just a little bit about how that works and why this should be a conjecture, but I'll go into it more later. So the point is that if this cyclic order of the vertex set actually gives you a Hamiltonian cycle, then there are certain combinatorial conditions under which you can define a rank 3 oriented matroid. And if that's realizable, then your graph is a visibility graph. And so the motivation, at least for this conjecture, is that Shor and Nev earlier have shown that it's NP-hard to determine if a rank 3 oriented matroid is realizable. But there is at least a source for this question of whether or not it's NP, and that was asked in the Ghosh Goswami survey paper. So we don't even know if this problem is NNP.
Sorry, Rose. So you have this connection with the realizable. So is it that you've got a subclass where it's the same, or just a sufficient condition in the subclass?
So I believe it's just a sufficient condition, and this is a difficulty having to do essentially with representations, whether or not you could have multiple different rank 3 oriented matroids which represent the same graph. But this leads to another natural question, which is that can we get our theorem to work in the case where this matroid isn't realizable, but just that the combinatorial conditions are satisfied? So we've been able to get that to work too. I'll go over what the definition is in a second, but we're just going to call these graphs pseudo-visibility graphs. So there's a connection between pseudo-line arrangements and oriented rank 3 matroids, but I'm going to give this definition in terms of pseudo-line arrangements instead, and then talk later on about where the matroid comes from. Okay, so the point is that the theorem still works in the pseudo-visibility setting, but there the natural conjecture, maybe still a little bold, but there the natural conjecture is that the recognition problem can be solved in polynomial time. And in this situation, O'Rourke and Strinu have shown that it is NNP. if the graph is Hamiltonian. And this is due to the connection with oriented matroids. Let me say a bit more about Jim's question, and that is that in some cases it's that specific matroid is realizable if and only if your graph is a visibility graph, but there's a little bit of extra information that you need that doesn't just come from the graph in order to get that. Okay. So first of all, what's a pseudoline? So a pseudoline is an image of a line under a homeomorphism of the plane. That's the way I like to think about it. So you're just squishing around the plane in different parts to get a pseudoline. But another way, yes?
I just wanted to ask quickly, is your second conjecture there given an ordering or not given the ordering?
Given an ordering, yes. Yeah. People have also studied these problems whenever you're not given an ordering, but it seems really difficult. So whenever we have, and actually, please everyone feel free to stop me, interrupt me as we're going through. I really like to have questions. It makes it feel more like a conversation as we're going through. Okay, so when another way to think about a pseudoline is as a simple curve that separates the plane into two unbounded regions. And that's going to be useful in a minute. So a pseudoline arrangement then is a collection of pseudolines so that each pair intersects in exactly one point where they cross. So the important factor here is that your pseudoline arrangement doesn't have to come from a homeomorphism of the plane, as in you can use different homeomorphisms for different pseudolines. And that's why it's helpful to just think of them as being curves. Okay, now in this picture, I have 4 points, and I have 4 choose 2 pseudolines, and each pair of points is in a unique pseudoline in the pseudoline arrangement. And from there, if I just remember the parts of the pseudolines that go between 2 of those points, then that part gives me what's called a pseudolinear drawing of K4. So this is definitely a drawing of the complete graph K4. And if I take a drawing of Kn, say, so that there exists a pseudoline arrangement of size n choose 2, so that every edge is a segment of a unique pseudoline in the arrangement, then that's called a pseudolinear drawing of K4. And so now if I take any such pseudolinear drawing of K4, and its vertex set is on the unit circle, say, then I can define a pseudo-visibility graph from that. So what I'm doing to define pseudo-visibility graphs is I'm taking a pseudolinear drawing of Kn, whose vertex set is on the unit circle, and I am saying that 2 of the vertices of Kn are mutually visible if the segment of the pseudoline between them is contained in the interior of the unit circle. So the way I like to think about this is that we're deleting segments which are on the outside, and we're deleting segments which touch the circle at a point other than the ends. And to get an ordered pseudo-visibility graph, we just also keep track of the cyclic order along the unit circle. Okay, so what if I want to show that every visibility graph is a pseudo-visibility graph. So we're really just getting more graphs whenever we do this. So to see that, let's start with the pseudo-visibility graph on the left and its Jordan curve in teal. And let's look at the line arrangement that that gives us. Then by the strengthening of the Jordan curve theorem, there's a homeomorphism of the plane which moves the Jordan curve to the unit circle, and the line arrangement becomes a pseudoline arrangement. And so that shows that every visibility graph is a pseudo-visibility graph. And Strinu has proven that you can't go the other way around. Not every pseudo-visibility graph is a visibility graph. And this might be obvious to some of the matroid theorists if you're just looking at pseudoline arrangements, but it's difficult for graphs because you might have different pseudoline arrangements which represent the same graph. So why is it that some pseudoline arrangements can't be moved to a line arrangement by a homomorphism of the plane? There's a nice answer for that. For those people who are familiar with matroid theory, this is a picture from Wikipedia. This is essentially the non-Pappus matroid, but we've drawn a pseudoline through these two vertices. And so there's no homomorphism of the plane, which makes all the lines straight at the same time. Okay, so to slow myself down, and because I've heard that you always have to put a joke in the talk, and I couldn't think of a joke, here's a picture of all of us at Bobby Agora in Poland. On the left, Tomek, myself, and James, and Bartek. And now so this is the theorem I've stated before. I'm about to go through some of the proof, so now's another time for me to take any questions.
Can you give me an example of a graph which is not a visibility graph?
I will. Actually, that's a really good question. Okay, so the easiest one is here on the right. So this is a 5-cycle, and it's Hamiltonian, so it's a cyclically ordered graph again. And so this is not a pseudo-visibility graph, and it's actually fairly difficult to show this. I like to think of the reason as being that every polygon has a convex vertex, but it's a little bit harder to show than that. So in general, if you give me any cycle of length at least 4, and you can find that as an induced subgraph, so that consecutive vertices are adjacent, then that is not a pseudo-visibility graph.
This is as an ordered graph.
As an ordered graph, yeah. Right, so that's one of our forbidden families. And so this is the way the proof goes, right? We're beginning by defining forbidden families. And for this whole segment, I'm considering our graphs as being cyclically ordered. So the other family is a little bit more complicated to describe, but that's the picture on the left. And the picture on the left actually does more for us. Interestingly enough, this thing on the right, if you exclude just the things on the right and you're triangle free, then you're exactly a Hasse diagram of a poset and you're not chi-bounded. So that's kind of interesting to me. It's just an aside. It kind of says this picture on the left is more important. So the picture on the left, what is it? Well, we say that two edges are crossing if in cyclic order they look like this. And so the picture on the left says that you have non-adjacent vertices, U and V, and you can start at V, and there's a sequence of crossing edges all along the top that gets you to U. And also on the bottom, there's a sequence of crossing edges that gets you to V. So I don't want to say what that is any more formally than that, but that's the idea for the other forbidden class. And by forbidden, I mean that you can't delete vertices in order to get either of these structures. Right, so the one at the right is totally induced, and it's okay if these things are edges in the one on the left. Okay. So the next main idea of the proof is that we're going to fix a vertex to be the smallest vertex, and we're going to look at the linear ordering, which that gets us. And in that linear ordering, we're going to find a partition of the vertex set into 3 parts, each of which induces what we're calling a capped graph. And a graph with a linear ordering is capped if whenever A is less than B is less than C is less than D, and you have these edges AC and BD, that then you must have the long edge AD. So I've drawn the obstruction on the top in the picture. Right, so it says that whenever you have edges which cross like that, then you have to have this edge above the top. So I want to give you some intuition for why this is in terms of polygon visibility graphs, because they're easier to work with and it's easier to really see what's going on. And in fact, this algorithm that I'm about to show is related to the window partition by Surrey, which is used to find really fast algorithms for shortest paths in these graphs. But what we do is we're going to fix some edge of the polygon, and we're going to consider this as being the smallest vertex, and then I'm going to go around in clockwise order. And now I'm going to take all of the vertices, which can see at least 2 points on this edge, which is highlighted at the bottom, and color all of those vertices blue. And now it turns out that all of those vertices induce a capped subgraph. So the point is, if you have an edge like this and an edge like this, then you also have to have the edge along the top. It's maybe not obvious why that is, but it works. And now we want to continue this procedure in each of the different parts. So each of those gives you a smaller polygon, and it has another edge that we're going to use as a base edge. And then we want the 3 color, so we have 2 colors left, which we're going to put next to this color, and we have to tell which of those to use. So what you do is you extend this edge all the way down, and then you look to see whether that polygon is on the left, like this one, and we'll use 1 color for that, or whether it's on the right, like this one, and we use a different color there. And so this is again on the right, and so we color it green. Now we continue the procedure. And the point here is that the things that are left uncolored can't see too far into the blue part. At most, they can see things that are on this edge. And so it essentially decomposes the rest, and we can continue the process. So I don't want to say too much about why this works, but that's the intuition. This is the procedure that we use. Okay, and the final step here is to color these cap graphs. Now we have one proof that lets us compute the Clique number exactly. You can reduce the problem of computing the Clique number to computing the Clique number of cap graphs. We have another proof which is really interesting, which relates to a really recent theorem of Scott and Seymour on undirected graphs. And so what this says is that if you have a graph like this, which is called a banana, it's a particular type of a banana. And if you look at the class of all graphs, which excludes every induced subdivision of a banana, then that class is chi-bounded. So this is a strong theorem. It's stronger than saying that classes with no long induced cycles are chi-bounded. And it turns out that cap graphs, once you forget about the linear ordering and you look at the undirected graphs, they exclude every induced subdivision of this particular banana. So I find that that's just sort of an interesting connection. It's not a very clear proof exactly, but it gives you a reason for why these are chi-bounded. It lets you get it as a corollary of this other result. So that's the idea of the proof, but for the rest of the talk, I really want to focus on this connection with oriented matroids. And there we have this conjecture, the recognition problem, and this is for ordered pseudo-visibility graphs. So we have I want to think about this conjecture that the recognition problem for ordered pseudo-visibility graphs can be solved in polynomial time. So due to some technical reasons, it's hard for me to state an exact theorem. So I want to consider sort of a subclass. And I think this is a nice way of doing it. So what we're going to show is that if you have a Hamiltonian graph excluding the below, that then you're an ordered pseudo-visibility graph. So let me say exactly what I mean by this. So we're considering our graph to be cyclically ordered, and that particular cyclic order gives you a Hamiltonian cycle, And in that cyclic order, you exclude all of these induced cycles of length at least 4. And furthermore, we're choosing some vertex to be our smallest vertex. And if you look at the linear order that that gives you, then that graph is capped, meaning it doesn't have this structure. So here's a picture that helps with that. Let's go back to this picture of a polygon. If you look at this first blue part we had, that has a cyclic order like this. And we know that in that cyclic order, your graph is Hamiltonian because all of these things are also edges. And we know that there's no induced cycle of length at least 4 in that order. And we know that the graph is capped because if you have 2 edges which cross like this, then you also get the edge above them. And so what this theorem says is that that combinatorial information is enough to show at least that you're a pseudo-visibility graph. So it's been shown that it doesn't characterize any particular type of polygon visibility graph. Maybe the pseudo part is necessary, but you get that much at least. So another thing which is nice about this is that you can test both of these properties in polynomial time. So you can certainly in time into the 4th test and see if you have this configuration on the left, but also you can test for these induced cycles of length at least 4 in polynomial time. So the way you can do that is you can guess 2 vertices that are next to each other with the rest of the cycle on one side, and then you delete all other vertices which are in triangles, and then you direct all edges in one direction, and then you look for a directed path. So you look for a directed path from A to B. So the point is that you can actually test for these things in polynomial time, and if you have enough, that's enough to show that you're a pseudo-visibility graph. Let me also say that you can characterize the type of pseudo-visibility graph that you're looking at essentially by having one edge which sees everything else. But I don't want to go into that, but you can view this as a characterization. Okay, so we want to prove that these graphs with those combinatorial properties are pseudo-visibility graphs. So in order to do that, we're going to need to define a pseudo-line arrangement. And we're also going to need to define a Jordan curve, which tells us what pairs are visible. So this is how we use the fact that the graph is Hamiltonian. Let me say that the cyclic order was 1, 2, 3, 4 for these 4 vertices. It turns out that if you define your pseudo-line arrangement correctly, then the edges between consecutive vertices have to be a polygon. And so what we can do is we can draw a Jordan curve just around the outside and then use a homeomorphism of the plane to get that Jordan curve to the unit circle. Right, so visibility just depends on this part, and then we'd use a homeomorphism of the plane to transform that Jordan curve into a circle, and that would define the visibility graph. Okay, so that's this point, is that we don't need to worry about the Jordan curve. So what that tells us is that we just care about essentially the combinatorial type of the pseudo-line arrangements. It's really enough for us to define the pseudo-line arrangements. Okay, and this is where the oriented matroid comes in. So what we're going to do, we want to construct an oriented matroid which represents the pseudo-line arrangements. This is the idea. So how are we going to do that? What sort of combinatorial information do we need that represents the pseudo-line arrangements? It turns out that it's enough to look at, for every triple, whether or not it occurs in clockwise order or counterclockwise order. So we're going to have a function By this notation, I mean the set of all ordered triples of 3 distinct vertices. So for each ordered triple of 3 distinct vertices, we're going to assign it a plus if that goes in the clockwise direction and a minus otherwise, in which case it's counterclockwise. So if this was just a line arrangement, we'd be able to say right away the ABC that look like this go in counterclockwise order, and the ABC that look like this go in clockwise order. But how do we do this for a pseudo-line arrangement? Well, if we start at A and walk along the pseudo-line to get to B, and then we have to turn right to get to C, then that is clockwise. And otherwise, whenever we walk along the pseudo-line from A to B, we have to turn left to get to C, and that's counterclockwise. So for every triple, we either have this plus or this minus. So we need to be able to axiomatize what exactly this means. There's a couple things to do for that. The first is that if you take C and move it to the beginning of the order, then it doesn't change whether or not it's clockwise or counterclockwise. So these are all the same. And now there are 6 permutations of 3 elements. So there are 3 other permutations remaining, and that those are all equal. And exactly one of these gets plus and one of these gets minus, is how you can axiomatize this. Okay, so we need a function that satisfies that property. Now there's another property we need, and this is more complicated looking. For those of you who are, I guess, familiar with oriented matroids, this is essentially the 4-term Pluco relation. So I finally got to learn what that really means. But let me say, first of all, what I mean by this notation. So I'm writing lambda AB as shorthand for phi of lambda AB is equal to plus. So this says that you encounter lambda A and B in clockwise order. So what I'm saying here is that for every distinct 5 elements, lambda, A, B, C, and D, if you start at lambda, and then if it's counterclockwise to go from lambda to A to B, and lambda from B to C, and lambda from C to D, and also from A to D and A to C, that then this final option of going from lambda to B to D is also clockwise. Okay, so that's what this last relationship says. Now, I want to say also that why did I choose plus here instead of minus? Well, one follows from the other. So it's not obvious why, but it ends up being true that saying this relation for the clockwise direction implies it for the counterclockwise direction. So let me just skip over that. So these axioms worded in this way are called a pre-CC system, CC for clockwise or counterclockwise. And they were introduced by Knuth in '92, and he already showed that they were equivalent to the axioms for oriented rank 3 matroids, where the underlying matroid is uniform. Okay, so first of all, what's the underlying matroid here? Well, for each triple, we either are positive or negative, and that means every triple is a basis. And so the underlying matroid here is really uninteresting. It's just U3N. And that at least intuitively makes sense because there's no pseudo-line containing 3 of these elements. So we just have no interesting circuits. Okay, and the clockwise, counterclockwise axioms say that if you take 3 elements and you take a permutation of positive sign, it doesn't change whether or not those are clockwise or counterclockwise. So that corresponds to that axiom of oriented matroids. And then finally, I mentioned that this is the four-term Pluco relation. So those are the three axioms for the chirotope of an oriented matroid, that the underlying set gives you a matroid, and then these other two things which relate to determinants are how I think about it. And so that means that phi is the chirotope of an oriented matroid. In fact, a uniform oriented matroid. Okay, and so from there, the Folkman-Lawrence theorem says that every oriented matroid, every rank 3 oriented matroid can be represented by a pseudoline arrangement. And so the point is that using this theorem, if you can find phi which satisfies, I guess, these two axioms, then that gives you a pseudoline arrangement. And so the whole proof just comes down to defining this phi. So I can give you at least the definition. Let me try and do that. So remember, we're considering that there's a linear order on the graph. And with respect to that linear order, you don't have this configuration on the left. So what I want to do in order to define phi of A, B, C is say that phi of ABC is positive if there exists an edge which contains B, as in it goes over B, and also one end of the edge is in this half-open interval, and the other end is in this half-open interval. So phi of ABC is positive if there exists an edge like that in the picture, and otherwise it's negative. And this is all I need to define phi, because now I can just define phi of, CBA to be negative phi of ABC. Okay, so this works. And I don't want to go into why this works, why this satisfies the four-term Pluco relation, but it's because of these forbidden configurations. Okay, so I want to go over the conjectures that we have, just a summary. So the first one is this really old problem of determining the complexity of recognizing ordered visibility graphs. And so I'd really like it if people from this audience could work on this question, because it's a really old problem, but most people have been trying to show that it's NP, that it is in polynomial time, I mean. And so I think that it'd be interesting to really try and show that it's NP hard instead. And then the other conjecture would be that recognizing ordered pseudo-visibility graphs can be done in polynomial time. And then finally, I mentioned at the very beginning, can you get a better approximation for the chromatic number this way? And for that, we'd at least conjecture that there's a polynomial P, so that every capped graph where we had this forbidden configuration, that every capped graph with clique number omega has chromatic number at most P of omega. And I should mention that this implies that the same thing holds for pseudo-visibility graphs, because remember, we reduced to the case of capped graphs. And finally, this conjecture is actually would be implied by a much stronger conjecture of Esperet, which says that every hereditary chi-bounded class has this property. So this conjecture, I think, seems sort of crazy. It says that as long as the chromatic number is bounded by any kind of crazy function of the clique number and your closed interleading vertices, that then your chromatic number is bounded by a polynomial of the clique number. And so this, I think, seems like it really kind of shouldn't be true, but I'd like to know. And our proof for coloring cap graphs directly is really tempting, because our proof actually lets you decompose any cap graph into omega minus 1 triangle-free cap graphs. So I've drawn in the picture a graph that has that property, that's capped. And what we do is we're able to partition the edge sets of a cap graph into exactly omega minus 1 parts, each of which is triangle free, but also capped. And so the point is that this is tight. This lets you compute the Clique number because you're able to delete one triangle free cap graph in a way that lowers the Clique number by exactly 1. And then you can continue this process. And so it really seems like the right argument for why cap graphs are chi-bounded. But the fact that it's an edge partition means that you are always going to get an exponential from doing this. And so, yeah, we'd really like to know if that could give you either a counterexample to the conjecture at the bottom or a proof of the thing at the top. Thank you.
Thank you. Any questions for Rose? So I got a quick question, basically following up from James's question. He asked if you knew of any graphs that weren't visibility graphs. Then you said yes, but yours was not an ordered visibility graph. So, and the one you gave actually was a visibility.
Right. Yeah, that's true. That's true. I feel like there must be something, but I can't think of an example. There are plenty of things which aren't cap graphs, but it becomes more difficult for visibility. And I think the question I'd be interested in there is, if you take a graph and subdivide it enough times, does it always become a visibility graph? And I think that might be true, which is sort of a weird property to have. James, I think we thought about this a little bit. Maybe James would have a better answer.
Yeah, it is true. If you subdivide enough times, then you become polygon visibility, or visibility rather.
Thank you. Yeah, that's really strange. For a chi-bounded class, it doesn't seem like you should have something like that. But it tells you, I guess, how important this partition is.
There was a comment in the chat just now about the art gallery problem as a subclass of NP.
Oh, sorry, I can't see chat. Oh, there it is. Yeah, so I didn't mention this explicitly, but one of the ways this has been studied in computational geometry is finding a minimum dominating set of a polygon visibility graph. And that's the art gallery problem. It's a subclass. That's interesting, yeah. So I guess that would suggest that maybe this problem, oh, it was a ways back, I'm not gonna be able to find it, but that maybe this conjecture at the top is actually an NP. Is that the suggestion?
Oh, yes, I think proving NP hardness is easy, but it's a long open problem where the art gallery problem is actually in NP.
So that would be interesting to see if that implies that this results that the art gallery problem is the existar complete. If that implies something about this. Yeah, so I haven't thought about this. I believe that these are still open. I've checked the papers that cite the survey paper, where the problem about whether or not recognizing ordered visibility graphs is NNP. And I didn't see anything there, but maybe you could get something about it.
This R, it's a complexity class. It's to decide whether a system of polynomial equations over the real numbers has a solution. yeah, I think it's a different criteria here. When you were talking about the ordered stuff, maybe you're using the Jordan curve or use some other terms to order them.
Right.
And then I think maybe it's not easy to, yeah, maybe it's easier. Maybe it needs to use a different criteria.
So yeah, in this paper that you mentioned, I'll definitely look at it. It seems interesting. In this paper that you're looking at, do they assume that the graph has an order to the vertex set that tells you what the polygon is?
Yes.
Right.
Yeah, I
That's
think
good.
yeah, that link to the paper, I don't think it had order. It's just a traditional one. It's just the traditional variability graph.
Right. Yeah. Yeah, no, that's interesting. It would be
Yes.
nice to
Thank
see
you
if there
for
was
the
a connection.
So for this second conjecture, if I don't give you the ordering, do you think it's probably hard then?
It
or-
has to be hard. Yeah, I would think so. I don't know why. I would think so. So I think that, yeah, I'd have to look this up. I think that for the top question, it's known in that case that it's NP hard if you don't have an ordering. But I'd have to check.
Any other questions?
Now, I'm still interested in this question about which graphs are visibility graphs. I mean, what's the smallest number of vertices that something can have if it's not a visibility graph?
Yeah, I don't know. That's a good question though. The first things that we started to look at were these intersection graphs of curves, because if you take any planar graph and you look at its one subdivision, then it's not an intersection graph of curves in the plane. And we tried to use that to see if all of those graphs, so we found that some of those graphs were visibility graphs. And so for that, we looked at things like the one subdivision of K5 and whatnot. And so that's the first thing I would consider going to for a small graph, which isn't a visibility graph, is something like the one subdivision of K5 or K33, but they, I believe, are. So.
And so you do know that there are infinitely many induced graph minimal non-visibility graphs, do you?
So for capped graphs, we know this, but for visibility graphs, we don't. So for capped graphs, the bananas are all also minimal, I believe. But yeah, no, I don't think we know much at all about this ordered visibility graph part unless you also ask that they're capped. But I mean, I find that really intriguing because you're just partitioning into 3 capped graphs. So from the coloring perspective, almost all of these are capped graphs, and really all the difficulty comes from capped graphs. But yet, yeah, we know very little about the forbidden induced subgraphs that aren't ordered. I mean, I guess the one thing I would be interested in looking at for that is, I don't even know what are the minimal graphs which aren't Hasse diagrams of posets. Because we had these 2 infinite forbidden families, and one of them was these cycles of length at least 4, which have that good ordering. And if you ask for that to be a linear ordering, then linear orders without this are exactly linear extensions of Hasse diagrams. Sorry, linear extensions of posets. And what I'm trying to say is that a graph has an order like this. And if and only if it's the Hasse diagram of a poset, and linear orders like this are in bijection with linear extensions of posets. I think that must be a hard problem.
Any other questions?
Yeah, I'm sorry to keep asking questions. But what was the issue about subdividing? James said something about subdividing.
Right, so that would be that every graph has a subdivision, which is a pseudo-visibility graph.
What about a visibility graph?
And also a visibility graph, yes. In fact, this is how the NP completeness proof, the fact that it's NP complete to show if the chromatic number of a polygon visibility graph is at most 5, the proof goes by starting with any 3 colorable graph and then finding a subdivision, which is a polygon visibility graph. I mean, they may have to do a little bit more to get the Hamiltonian cycle, but it's essentially the same idea.
Thanks.
Okay, so if there's no other, oh, there was another comment in the chat from James.
All right.
Yeah, it's just a graph that I don't think is a visibility graph, but it's not a small example.
Wait, so what do you mean for each edge at a degree 2 vertex? Is it?
Keep the edges between the 5 vertices of a cycle.
Ah.
So you've got a bunch of triangles.
What does it mean by blow it up a couple of times?
So you take the graph and then substitute at each vertex that same graph. I think.
Then you're going to connect things to all the copies.
Yeah, and for the edge, you just have
Okay.
every edge between the 2 graphs. I think that's not visibility.
Or you have any insight to tell us why?
I think because you shouldn't be able to partition it into 3 capped graphs.
Okay.
So I think just this first graph is not capped.
Right.
And then the blow-ups make it so that you don't get this partition.
Nice, okay.
Because these 2 degree 2 vertices are kind of there to give you an ordered whole, is the idea.
Okay.
There you go, James. Other James.
Thank you.
That would be cool.
All right, I'll stop the recording.